Hi, and welcome to Quantum Mechanics Revision 1. As a lot of you have requested revision in quantum mechanics, I thought a good first video might be all the conservation laws. These sort of underpin a lot of what follows, and they're a good way of just sort of reminding ourselves of all the key concepts as we move into quantum mechanics as a whole. So, pause the video. How many conservation laws can you name? Well, there's a fair few, and most of them are written up there, so if you can read my handwriting, you should have got them. But let's go through them. We start with conservation of momentum. Pause the video, think for a second. When does conservation of momentum come up in quantum mechanics? Well, conservation of momentum, as I often say, is probably the most important law in the universe. This seems to be the one that you've got the least wiggle room on. And I think where this really interfaces with quantum mechanics is in annihilation and pair production. Now we know that whenever annihilation happens, there has to be a particle and its corresponding antiparticle. They will annihilate, and therefore whatever momentum they had beforehand will cancel each other out. Similarly, whenever we do pair production, particles coming into existence, we always create a particle and its corresponding antiparticle, same mass, moving in opposite directions at the same velocity. Therefore, all we had before was energy with no momentum. Afterwards, we've got two similarly sized particles moving away from each other. Therefore, overall, they have no momentum, because this momentum cancels out this momentum, and therefore, momentum is always conserved. So that's where it really interfaces with quantum mechanics. Next, we have energy. Okay, pause the video for a second. Is energy always conserved? The answer is, of course, no. It isn't energy per se, but instead mass energy equivalence is always conserved using, pause the video again, which equation? Correct. E equals mc squared. I don't know if I said why I correct, I just assumed you got it right at home. So, mass energy equivalence always conserved. What does this mean? Well, it means that whenever mass turns to energy or energy turns to mass, we always get the same input and output. So therefore, radio waves don't just turn into mountains, but sometimes very, very energetic cosmic rays, really, really high energy stuff, turns into particles around the size of kaons. So that's sort of our mass energy equivalence. And this whole thing of mass energy must be conserved. So if we're losing mass, we'll be gaining energy. If we're gaining energy, we'll be losing mass. So that has to be conserved, but energy by itself doesn't. Okay, next one. Charge. Charge, nice easy one here. It's a property of some quarks that they have charge, and the total charge is always conserved. And this should also tell you that a particle and its antiparticle have to have opposite charges, because if energy is turning into a particle-antiparticle pair, we've got no charge at all with the energy, therefore whatever charge we create on the particle, the antiparticle has to have the opposite charge. That's a good way of remembering that. If that weren't the case, conservation of charge would not hold. Okay, lepton number. There is an interesting wrinkle when it comes to lepton number. Pause the video, see if you can remember it. The wrinkle when it comes to lepton number is that there are two different ones, electron lepton number and muon lepton number, and they both must be conserved. So our electron lepton number must be the same before and after, and our muon lepton number must be the same before and after. What does that mean in practice? Well, an electron has an electron lepton number of 1, meaning that if we have an electron on one side and it's going away, on the other side we're probably going to need an electron neutrino, which also has an electron lepton number of 1. So if this is going away, we'll need a neutrino just to balance it out. Similarly, if we have a positron, which has an electron lepton number of -1, we're probably going to want an anti-electron neutrino on the other side, which also has an electron lepton number of -1 in order to balance that out. Exactly the same things with muons. We've been through this a few times, but good to just remind ourselves. Now we move on to baryon number. Think for a moment, what has baryon number? The answer is not baryons. And what number is it? Just pause the video, have a little think. The answer, of course, is quarks, with each quark having a baryon number equal to a third, and each anti-quark having a baryon number equal to minus a third. So if you have three quarks together, we'll have one baryon, and we'll have a total baryon number of 1, and similarly an anti-baryon will have three anti-quarks together, and therefore we'll have a baryon number of -1. And this again must always be conserved. Now the neat thing about baryon number is when we get to pions. Pions, of course, are created with a quark-antiquark pair, which means we're going to have a third and minus a third. So overall, each pion is going to have a baryon number of 0, which is useful because it means you can kind of add them or take them away as often as you want, and it's not going to affect the baryon number. So you can just throw in pions as much as you want. Doesn't affect that part of the conservation laws. Also, if you think about it carefully, because it's a quark and an antiquark, they'll often have a charge of 0, meaning that normally all we're really looking at is the mass energy equivalence when we're talking about adding pions or taking pions away. Finally, we have strangeness. Pause the video. When is strangeness conserved and not conserved? The answer, of course, strangeness is always conserved unless we are having a weak interaction, in which case strangeness is not conserved. And often in exam questions, remember, they'll ask, how do you know the weak interaction happened? And you can go, aha, look, strangeness is different before and after, therefore the weak interaction must have happened. So strangeness is an odd one because all the others are always, always, always conserved. This one is sometimes conserved, who knows? So there you go, conservation laws. Right, we'll be continuing from here tomorrow. Do the questions underneath. Have a good one.